All right. So, hi everyone, people living at home today. We really miss you, right? And we're going to discuss. We were discussing fast Fourier transforms in the last class. And what are fast Fourier transforms? Fast Fourier transforms are essentially a fast way to compute discrete Fourier transforms, right? And what are discrete Fourier transforms? You can get it from this particular relationship. This is just gives you a representation of a signal in the frequency domain, right? So if you have an n length signal, x of n, so going from 0 till n minus 1, so you can find its DFT by this relationship. So x of k, which are the DFT coefficients, is just n going from 0 till n minus 1, the sum x of n times e to the power minus j 2 pi k n over n, right? Now we discuss why do we need a fast algorithm to compute the fast Fourier transform, or to compute the DFT. Reason being that, let's say, if you take the example of multiplication or complex multiplications, because generally multiplications and complex multiplications, these are the most computationally intensive part, right, in computers or DSP processors. So let's say if you take one DFT coefficient, right, so to compute one DFT coefficient you need n complex multiplications, right? So if you just expand the sum, this is sum over n components, so you need like n complex multiplications. And for n DFT coefficients you would need n squared complex multiplication, and that's a big number, right? Let's say you have 1024 length signal. So 1024 length signal, you have where is this, the pointer? Yeah, so you have 1024 squared, so that is like approximately 1 million complex multiplications. FFT on the contrary reduces number of complex multiplications to n over 2 log 2n. So it reduces them to n over 2 log 2 of n. So that means in place of 1024 squared complex multiplications, we would just have n over 2, this 1024 over 2 log 2n of 1024, which is 2 to the power 10. This will be just 5120. So we all agree, 5120 is much better than 1 million, right? So for that reason we need this complex this DFT algorithm, this FFT algorithm, to have a fast way to compute the discrete Fourier transform, right? The only and we are going to discuss the discrete Fourier transform, the decimation in time FFT algorithm of base 2, right? Why do we need it for base 2? I mean, we will see how the algorithm is set up soon. The only caveat of this algorithm is that the sequence length has to be of the power of 2, right? That means it has to be something like 2 square, right? Let's say 2 squared, 2 to the power 3, 2 to the power 4, and so on and so forth, right? It has to be something of the power of 2. Now, is that a problem? Not really. If you have a sequence, for example, of length 10 long, so what you can do, you can just append zeros or add zeros next to the sequence such that from 10 it becomes 16, right? And you can then compute the DFT using the FFT algorithm. But since you are appending only zeros, let's say for example if you had x of 0, x of 1, right, and so on and so forth, x of 9, but to get to 16 coefficients you can just add these 6 zeros, 1, 2, 3, 4, 5, and 6, and then you can compute the DFT of this entire thing. Now you have 16 points, so that means you can compute the DFT. But since you have appended zeros, does that have any effect? Not really, because you're just adding zeros, and adding zeros is just adding nothing, right? The only difference would be that we know that the DFT is a sampled version of DTFT algorithm, or DTFT, where the samples are taken at 2 pi k over n. So what we are doing by appending zeros, we are just increasing this n. So that means we are just sampling the same DFT spectrum but a bit more finely. But if our goal is just to analyze the frequency domain representation of the signal, we can just have a finer sampling of the DTFT spectrum. We can just analyze that, because that's not an issue. Okay, that we discussed. see why the Wacom tablet is creating a bit of a problem. Okay. Yeah, now it will be fine. All right. So why do we need things of base 2? The reason is very simple. In the FFT algorithm, we have this divide and conquer approach, right? What is the divide and conquer approach? If you are a colonizing country, right, and you want to conquer a country, you can try finding different factions inside the country and make them fight each other. So their combined strength is going to be, weaker. So then you can just conquer the country. But in the context of DSP, what is divide and conquer? You divide the problem into smaller, simpler problems, and you solve those problems instead. So let's say if you have an endpoint DFT, right? So let's say this is the endpoint DFT block that just computes the endpoint DFT of these n inputs. The input is a signal and the output is DFT. Now, the basic idea behind FFT is that you have the same length input, but you do something to the input such that the output then you give to two n over 2 point DFT blocks, in a way that first you get the even coefficients of the DFT, even index coefficients of the DFT, and next you get the odd index coefficients of DFT. And if you can do it once, you can do it multiple times as well. So for instance, you have a 16 point DFT, you can break it up into two 8 point DFTs, then each one of them you can break them up into two 4 point DFTs, right? So each one of them, and then each 4 point DFT you can break those up into two 2 point DFTs. Clear? And then what is a 2 point DFT? 2 point DFT is very simple, right? If you have two inputs, the even index DFT coefficient of a 2 point DFT is just the addition of the two inputs, and the odd indexed DFT coefficient for a 2 point DFT is just a subtraction of second input from the first one. So this is a 2 point DFT, right? So this is the very simplest case, right? So this is what we will reduce our problem to at the very end. Clear so far? Yeah. So this is just a quick recap, right? So bottom line, we just need to understand how we can break up an n point DFT into two n over 2 point DFTs. That is the bottom line. Because if we can do that, then we can divide them further into two n over 4 point DFTs, then we can divide them further into n over 8 point DFTs, and so on and so forth. So the answer to that problem lies in this definition of the DFT. Just begin with the definition of DFT. Just replace e to the power minus j 2 pi over n with w subscript n, just for ease of writing, right? And then just have the same relationship. Just replace e to the power minus j 2 pi over n with w subscript n. You have x of n times w subscript n to the power kn, because this is what is left over here. And then what we did here, we just broke the sum up into two subsections. One section goes from 0 till n over 2 minus 1, and the other one goes from n over 2 till n minus 1. We didn't do anything. Like for example, if you have, let's say, a sequence 0 plus 1 plus 2 plus 2 plus 3 plus 4, so you can just combine, or plus 5, right? So you can combine these together and these together, and then you add them, right? It doesn't make any difference. Okay. All right. So then what we did, we just took this part, and in this part we made a substitution. We said let's substitute n minus n over 2 with p. In other words, we have n equals p plus big N over 2. Yeah. So we just replace n with p plus big N over 2, and that is what we are doing over here. So then if n is n over 2, so p is n over 2 minus n over 2, that is 0. And when n is n minus 1, p is n minus 1 minus n over 2, which is n over 2 minus 1. That means the limit of this sum will go from 0 till n over 2 minus 1. And then in place of n, we can just plug in p plus capital N over 2. We have it over here, w subscript n to the power k p plus big N over 2. So that is what we have over here, because in place of n, we just put p plus big N over 2. So then this can be, broken up into w subscript n to the power kp times w subscript n to the power kn over 2. And then if we just have a look at w subscript n to the power n over 2, that is this one, w subscript n is e to the power minus j 2 pi over n, that to the power n over 2. So this cancels, and what you are left with is minus 1. And w subscript n to the power k times n over 2 is just minus 1 to the power k. So then you just have minus 1 to the power k, and then you just, what you did, you said that okay, this p is just a dummy variable of summation. It does not matter if you replace with q, you will get the same terms, and it does not matter if you replace with n, you will get the same terms again. So you just replace with n, and then this is what you get, and this was what with what you started. So you just replaced this thing in the original equation with this thing, right. So that is what you got over here, right. Now clearly you have two cases here. One case is when this k is even, and the other case is when this k is odd. When this k is even, minus 1 to the power e1 is what? Is you have, let's say, k equals 2. What is minus 1 to the power 2? 1. If k is, let's say, 4, what is minus 1 to the power 4? 1, right. So whenever k is even, minus 1 to the power something even is 1. Whenever k is odd, minus 1 to the power something is minus 1. So you said, okay, what we are going to do, we are going to replace k equals 2m for even cases where this m goes from 0, 1, 2 up until n over 2 minus 1, right. So that means, when k m has the value 0, k will have the value 0. When m has the value 1, k will have the value 2. When m has the value 2, k will have the value 4. So when m goes from 0, 1, 2 up until n over 2 minus 1, k goes from 0, 2, 4 up until n minus 2. Similarly, the odd case, we can represent it by saying k equals 2m plus 1, where this m again goes from 0, 1, 2 up until n over 2 minus 1, and when m goes over these values, k goes from 1, 3 up until n minus 1. Clear? So far so good? Any questions? Clear? Alright. So what we are going to do, we will just do the even case first, then we will do the odd case, and then we will see what kind of values do we come up with. So let me just copy this guy, just copy this. I guess I can just copy this whole thing. Let me move on to the page for today. I say view 100% and that's fine. Then I say here, let me just so I just brought this stuff from the previous set of notes, right. So I'll just have a look at this expression. I'll just replace k with 2m, right, and I'll simplify this. Questions till this point? Okay. So let's move on. So for even case, I am going to put k equals to m. So then I will have thickness. Yeah. Then I will have x of 2m equals. So I am just replacing k with 2m. So wherever I have k, I will just replace it with 2m equals the sum n goes from 0 till n over 2 minus 1. Then I have x of n w subscript n to the power. Here I have k times n, right. So, in place of k times n, I will just replace it with 2m n, and then I have plus minus 1 to the power k over here. So, in place of minus 1 to the power k, I will just replace it with 2m, and then I have this sum again, but only place where k appears is over here. So, I will have n going from 0 till n over 2 minus 1 x of n plus big N over 2. Then I have w subscript n to the power k n, but k I am replacing with 2m, so 2mn. So, all what I did, I just took this expression and I just replace k with 2m, that is it, no other stuff happening. Questions at this point? All right. So, then I'll just simplify this guy. I have x of 2m equals n goes from 0 till n over 2 minus 1. I have x of n w subscript n to the power 2mn, and then I have minus 1 to the power 2m, right. So, this is always positive. So, this is just plus 1, and then I have n going from 0 till n over 2 minus 1 x of n plus big N over 2, and then I have w subscript n to the power 2mn. Now, question, are the limits the same for both the sums? Yeah. So, that means I can just combine the sums together. So, I can just write this as x of 2m equals n going from 0 to n over 2 minus 1, and then when I combine the two sums together, this w subscript n to the power 2mn, that is common. So, I can write this as x of n plus x of n plus big N over 2, and then this w subscript n to the power 2mn. Clear? Excuse me. And this thing I can write as n goes from 0 till n over 2 minus 1, and in place of this whole thing, I can just replace it with a of n times w subscript n to the power 2mn. Where this a of n is equal to just x of n plus x of n plus big N over 2. And in this sequence, this n goes from 0, 1 up until n over 2 minus 1, because you see this sum is going from 0, 1 up until n over 2 minus 1. Clear? Okay. Now, before we move further, let us see this guy w subscript n to the power 2, because that is what we have here, w subscript n to the power 2. What is this? Now, we already have chosen w subscript n to the power e to the power minus j 2 pi over n. Yes. So, w subscript n to the power 2 from the definition that we have had earlier is just e to the power minus j 2 pi over n to the power 2. Clear? Or you can also write it as e to the power minus j 2 times 2 pi over n. Yeah. So if you have something like 2 times 2 pi over n, is it the same as 2 pi over n over 2? It's the same, right? So then I can write this as e to the power minus j 2 pi over, or let me write it bigger way, e to the power minus j 2 pi over n over 2. This is w subscript n to the power 2. Clear? Clear? Yeah. Okay. Now by definition, w subscript n is e to the power minus j 2 pi over n. So whatever subscript you have over here, you brought it over here. Whatever subscript you have over here, you brought it over here. Or whatever subscript you had here, you brought it over here. So similarly, I can also write this as w subscript n over 2. Because what is w subscript n over 2? It's just e to the power minus j 2 pi over n over 2. And that is exactly what I have here. Does that make sense? Yeah. So this is it. So w subscript n to the power 2 is just w subscript n over 2. So I can just plug this back in here. I can do that, right? Can I? Can I not? Yeah, I can do that. Right. Okay. So let's do that. So then I would have x of 2m, again the sum, n going from 0 till n over 2 minus 1, n going from 0 till n over 2 minus 1, a of n w subscript n over 2 to the power mn, where this m goes from 0, 1 up until n over 2 minus 1 excuse me, and you have a of n is x of n plus big N over 2, where this n goes from 0, 1 up until n over 2 minus 1 for this sum, and this is what you have. Clear? Clear so far? All good? Okay. So this was for the even case, right? Let's see the situation for the odd case. For the odd case, we'll just repeat the same thing, replace k with 2m plus 1. Replace k with 2m plus 1, where m goes from 0, 1 up until n over 2 minus 1. Excuse me. So then you have, so this was the original expression, this guy. So just replace k with 2m plus 1. So x of 2m plus 1 is equal to, we have the sum n going from 0 till n over 2 minus 1, and then inside the sum you have x of n w subscript n to the power k n. So all what you need to do is just replace k with 2m plus 1, that's it. So you have x of n. In the original one you had w subscript n to the power k n, so in place of k n you just write 2m plus 1 times n. Then you have plus minus 1 to the power k. Here you had minus 1 to the power k, and then you have this thing. So just write n goes from 0 till n over 2 minus 1. You have x of n plus big N over 2, and then you have w subscript n to the power kn, which is 2m plus 1 times n. Okay. So now, I mean, again, it's just simplification, right? So this is just n goes from 0 till n over 2 minus 1. Then you have x of n. Then you have w subscript n to the power n, and then you also have w subscript n to the power 2mn. You just broke this thing up. And minus 1 to the power k when k is odd, which is just 2m plus 1, is always minus 1. So this is just minus or plus minus 1, right? And then you have n goes from 0 till n over 2 minus 1, x of n plus big N over 2, then w subscript n to the power n again, and w subscript n to the power 2mn. So now, you know, since this is just minus 1, so I can just replace it with just minus over here, right? And again, are the limits of the sum the same? The limits are the same, right? So then I can just combine them together, n going from 0 till n over 2 minus 1, and then I have x of n minus x of n plus big N over 2, and then I just took w subscript n to the power n and w subscript n to the power 2mn common. Now, we already established earlier that w subscript n to the power 2 here, w subscript n to the power 2 is just w subscript n over 2. So that is what I will write over here. I can just write this as n going from 0 till n over 2 minus 1. And in place of this thing, x of n minus x of n plus big N over 2, I'll just write b of n. Then I have w subscript n to the power n, and then w subscript n over 2 to the power mn. What is this b of n? This b of n is just x of n minus x of n plus big N over 2. And for this one, n goes from 0, 1 up until n over 2 minus 1, and also this m over here goes from 0, 1 up until n over 2 minus 1. So these are the odd index DFT coefficients. Because you put m equals 0, you will get x of 1. You put m equals 1, you will get x of 3, right? So these are the odd index DFT coefficients. Questions till this point? All good? Clear? Clear so far? Let me rewrite these even and odd index DFT coefficients. I will just copy these. I have just x of 2m, which is just a sum, n goes from 0 till n over 2 minus 1, and I have a of n times w subscript n to the n over 2 to the power mn. Similarly, I have x of 2m plus 1 equals the sum, n goes from 0 till n over 2 minus 1, b of n times w subscript n to the power n times w subscript n over 2 to the power mn. Let me just combine these two expressions. I just copied this entire thing over here. That's it, nothing fancy, right? Where for both of them this m goes from 0, 1 up until n over 2 minus 1. Okay, now you compare these equations with the definition of DFT. So, what was the definition of DFT that we began with? The definition of DFT that we began with was something like x of k equals n goes from 0 till n minus 1. This is for an n point sequence, x of n w subscript n to the power kn, where this k goes from 0, 1 up until n over 2 n minus 1. So, this was the definition of DFT, right? So, this is DFT definition. So, how long is the signal x of n here? How many points does it have? The signal x of n, how many points does it have? I am summing up over how many points? No, it goes from 0 till n minus 1, right? So, how many points are there between 0 and n minus 1? N points, n points, right? I mean, these are discrete, right? Going from 0 to n minus 1, you have n points, right? So, this sequence x of n is of length n long, is of length capital N long. Is this clear? Yeah? Okay. So, then you have, what do you have here? You have the sum over all these points, and you are summing the product, the sequence values times w subscript n to the power kn. So, what is k? K is just the index for the DFT coefficient, that is it. K is just the index for the DFT coefficient. And what is n? N is just going from 0 to the length of the sequence. What is this capital N? Capital N is just the length of the sequence, and you have that in the subscript. Now, you compare this expression with this one. What do you have here? You have the sequence A of n. How do you define the sequence A of n? You define it with this relationship, x of n plus x of n plus n over 2. So, basically you divide the signal into two sections. You take this half, you just sum them, right, the corresponding entries. Now, how long is the sequence A of n? What values of n is it going over? Going from 0 till n over 2 minus 1, right? So, what is the length of this signal A of n then? It is not n. Yeah, okay. You take, so this is the entire signal, right? You take one half, take the other half, add them together to corresponding. So, you add the corresponding values. So, the sum signal will be how much long? If you just take this, for example, you have, suppose these are two halves of the signal, right? And this is this long. I just took this half, added it into this one. So, what is the remaining length? No, this is going from, let us say this is going from 0 till 15. So, there are 16 points, right? We took these 8 points, added them into these 8 points. So, what is the length of this sequence now? 8 points, yeah, that is it, right. Similarly, here you can see this n is going from 0 to n over 2 minus 1. So the length of this sequence is how much? Is n over 2, right? Okay. Now if you see this one, then this sum is going from 0 till n over 2 minus 1. That is, this sum is going over all the points of the sequence, right? Here x of n was length capital N, a of n is length capital N over 2. So this, for that reason, this sum is going from 0 till capital N over 2 minus 1. And then you have this twiddle factor w. Here the base was the number of points n, and here again the base is number of points, because the points is now half. So for that reason you have capital N over 2. Here you have mn, here you have kn, n is the same, right? And m is just indexing the DFT coefficient. Same story. So can I then say that this guy x of 2m is just the DFT of the sequence a of n with n over 2 points? Can I deduce this result from here? So x of 2m is just the DFT of the sequence a of n with just n over 2 points. So it's the DFT of half the points. Does that make sense? Clear? So it's just DFT of the half the points, right? Similarly, I can say that these ones, x of 2m plus 1 is just the DFT of the sequence b of n times w subscript n to the power n, again with n over 2 points. So I just take this one, this is just the sequence b of n times w subscript n to the power n, right? If you multiply these, you will just get one sequence, right? And the length of that sequence is going to be n over 2. And this is just the same that you have for the DFT formula. So this is just the DFT of the sequence b of n times w subscript n to the power n with n over 2 points. So moral of the story, you broke this n point DFT into these two n over 2 point DFTs. Is that clear? Yeah, you broke this n point DFT into two n over 2 point DFTs. So all what you need to find is just need to find the sequence a of n and the sequence b of n times w subscript n to the power n. If you have that, you get the DFT, right? You get the even index coefficients for this guy, and you get the odd index coefficients of the DFT for this guy. Okay, this one, for example, you will get x of 0, x of 2, x of 4, x of 6, x of 8, and so on and so forth, right? Here you will get x of 1, x of 3, x of 5, x of 7, and so on and so forth. Is that clear? 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 Okay. And let me just show you guys the slides. So that means, when we were talking about doing something to the input here, right? So we were talking about here, starting from an n point DFT, how we can get two n over 2 point DFTs. So here you just find the sequences a of n and b of n times w subscript n to the power n, and then you sequence a of n, you put it in this n over 2 point DFT, it will get you the even index coefficients. The sequence b of n times w subscript n to the power n, you put it as input to this n over 2 point DFT block, and you get these odd index DFT coefficients. Does that make sense? Clear? Abu Bakr? Clear? Yeah? Good? Okay. Moving on. Let me just show you the slides. Where are the slides? These are the slides. All right. Now, this may look a bit daunting. Let me just bring it in the notes. But don't worry, it's not that complicated. So before we look at the dangerous looking diagram downstairs, right? You just have a look at these ones, right? These are just symbols, right? Just some notations saying that, let's say if you have two arrows and they are converging at one point, you're just doing the sum of the two inputs, right? If you have two arrows converging at one point, but one of them has -1 over here, that means just one of the inputs is being subtracted from the other one. So the output from here is x minus y, right? Similarly, if you have just something written under the arrow, it's just this term multiplied by the input, and that is the output. This is just a scaling operation, right? Now let's say this is that something that we talked about here, right? This something is what we have over here, not here, here. This is an n over 2 point DFT, this is an n over 2 point DFT, right? And the output is the even index DFT coefficients, and here the output is the odd index DFT coefficients, right? Now forget about this thing down below, right? Let's just forget about this thing. Let me use a different color marker. Let me use this one, right? So let's just forget about this guy for now. It disappeared. Right. Let's forget about it. So to get the even index DFT coefficients, this is an 8-point DFT, right? For that reason, the even index DFT coefficients are x of 0, x of 2, x of 4, and x of 6. You need to have the sequence a of n at the input. And what is the sequence a of n? A of n by definition is just x of n plus x of n plus big N over 2. Let me write it. So a of n is just x of n. I think I should write it down below. So a of n is just x of n plus x of n plus big N over 2. Now here, what is this big N? Big N is the total number of points whose DFT I am computing. So what is the total number of points whose DFT I am computing? 8, right? So this big N is 8. But this n in this case goes from 0, 1 up until n over 2 minus 1, that is 8 over 2 minus 1, that is 3. 0, 1 up until 3. So I need to get a of 0, a of 1, a of 2, and a of 3. So a of 0 will just be x of 0 plus x of 0 plus big N over 2, that means 4. A of 1 is going to be x of 1 plus x of 5. A of 2 is going to be x of 2 plus x of 6. A of 3 is going to be x of 3 plus x of 7. Clear? So let's see if that is indeed the case. Here you have a of 0, right? So a of 0 by definition should be x of 0 plus x of 4. So this is x of 0 and this is x of 4. So this is x of 0 plus x of 4. X of 1, a of 1 is just x of 1 plus x of 5. This is x of 1 and this is x of 5. A of 2 is just x of 2 plus x of 6. So this is x of 2 and this is x of 6. Yeah. A of 3 is just x of 3 plus x of 7. So this is x of 3 and this is x of 7. So this indeed is the sequence a of 0, a of 1, and a of 2, and a of 3. This is indeed the sequence a of n. This is the complete sequence. Oops. Yeah, this is the complete sequence a of n. This whole thing is just a of n. Clear? So now let's look at the other one. Here I need to get the sequence b of n times w subscript n to the power n. So what is sequence b of n? B of n is just x of n minus x of n plus big N over 2. So that means what is b of 0 is just x of 0 minus x of 4. what is b of 1 is x of 1 minus x of 5 and so on and so forth. Clear? Now here let us see if that is indeed the case. B of 0 is x of 0 minus x of 4, because you have this minus over here. B of 1 is x of 1 minus x of 5. B of 2 is x of 2 minus x of 6. B of 3 is x of 3 minus x of 7. So this indeed is the sequence B of n, and then I can multiply it with w subscript n to the power n. So this one just this is b of 0, so w subscript n to the power 0, b of 1 w subscript n to the power 1, b of 2 w subscript n to the power 2, and b of 3 w subscript n to the power 3. What is w subscript n? Is just e to the power minus j 2 pi over n, and in this case is w subscript 8, so e to the power minus j 2 pi over 8. Clear? Questions till this point? All good? All is clear? Yeah? Okay, good. Yeah. I will not want you to write the copy this thing, but as long as you get the basic idea, it's fine. Okay, so moving on, let's look at this guy, right? Let's just make that here. So we have as input, you have a of 0, a of 1, a of 2, and a of 3, and you are giving that as input, right? This guy, right, is coming as input, and the output is x of 0, x of 2, x of 4, and x of 6. Clear? Clear? Yeah? Okay. Now, for the purpose of understanding, right, I'll just change the notation slightly, right, because now this thing is the new input to this 4-point DFT block, and this is the new output, right. Now what I need to do, I need to do the same process again, but the way I'll do that, so when I'll do that, I'll repeat the same process again. I'll get the even indexed coefficients first, so even coefficients first, and the odd index coefficient second. Now in this case, the sequence is this one, the output sequence is this one. So what are the even coefficients for this one? This one and this one, because this is like coefficient number 0 and this is coefficient number 2 for this particular sequence, right. This is coefficient number 1 and this is coefficient number 3 for this particular sequence. Yeah. So now in this case, coefficient number 0 and coefficient number 4, they are the even index coefficients, and these ones, for the purpose of this particular case, these are the odd index coefficients. And in this case, this n is what? So how many points do I have at the input? 4, right? So this n is 4. Clear? I can call this the new input. I can just say this input, let us say x hat of 0 is this one, x hat of 1 is this one, x hat of 2 is this one, and x hat of 3 is this one, right. And these are the outputs. So capital X hat of 0 will be this one, capital X hat of 1 will be this one, this is capital X hat of 0, this will be capital X hat of 1, this will be capital X hat of 2, and this will be capital X hat of 3. Clear so far? Clear so far? Yeah. Okay. So now I would need to get the new sequences a hat of n and b hat of n times w subscript n to the power n, because now this a hat of n will just be x hat of n plus x hat of n plus capital N over 2, and in this case is going to be x hat of n plus x hat of n plus capital N, in this case is 4, it is going to be 2. That means a hat of 0 would be x hat of 0 plus x hat of 2. A hat of 1 is going to be x hat of 1 plus x hat of 3. A hat of 2 is going to be, no, it is not going to be a hat of 2. Why? Because this sequence a hat of n will only go from 0, 1 up until n over 2 minus 1. What is capital N in this case? 4. So that means this just goes from, so capital N over 2 minus 1 is going to be 4 over 2 minus 1, that is just 1. This n will just be 0 and 1. So to get a hat of 1, I will just need to combine this term with this term, right. To get a hat of 2, I will just need to combine this term with this one. So when I do that, basically I am combining the term at n with the term at n plus big N over 2, the term at 0 with the term at big N over 2, the term at 1 with the term at 1 plus big N over 2, the term at 2 with the term at 2 plus big N over 2, and so on and so forth. Yeah. So then the same guy, you can write this as this input, you have these inputs. The outputs, like we just established, we will get the even index coefficients first. So x of 0 and x of 4, and we will get x of 2 and x of 6, right. And how are we going to get them? So we would need to, so this is, let us say, the outputs of 2 point DFT, because n over 4 point DFT, right, and this will be the outputs of 2 n over 4 point DFTs, right. So first I need to get the sequence a hat of n. So I need to combine this guy with the one over here. So this is x hat of 0, x hat of 1, x hat of 2, x hat of 3. So get a hat of 0, I need to have x hat of 1 plus x hat of 2. So x hat of 1 plus x hat of 2, which is this guy. Similarly, this is a hat of 0. A hat of 1 will just be the term at 1 plus n over 2, which is this one, 1 plus 2 is 3. So this guy combined with this guy. Yeah, this will be a hat of 1. Similarly, I need to get b hat of 1 and b hat of 2. So b hat of 0 and b hat of 1. So b hat of 0 is going to be just this guy, and from here I just subtract this guy. Similarly, b hat of 1 is going to be just this guy, and from here I subtract this guy, this b hat of 1. But I would need to multiply them with w subscript n to the power n as well. That means w subscript 4 to the power 0 and w subscript 4 to the power 1. Clear? Questions till this point? Okay. Now what is this? This is, if this capital N was 8, so 8 over 4 is 2, right. So this is just a 2 point DFT. And you already know what is a 2-point DFT, right? Let me just copy this guy. Control C. Let's have it here. Right. And you already know what is a 2-point DFT, and that we discussed in the last class. A 2-point DFT, the first coefficient is just the addition of the two inputs, and the second one is just subtraction of second one from the first one. That's it, right? So I can just replace this guy. I can just add these two together, and then I can just subtract this one from this one. Similarly, I can add these two together, and then I can subtract this one from the top one. Clear? And this is exactly what you have in your slides. This guy. This guy. Let me just zoom in. So this whole thing, and this, by the way, x hat of 0 is basically a of 0, right? This is a of 1, this is a of 2, and this is a of 3, because this is what we said over here, right? We said a of 0, I renamed it to be x hat of 0 because this was the new input, right? And this whole thing, this thing, right? This thing is the same as what you have over here. Yeah. So this was the same as this guy, right? You can just say this whole thing is the same as the one above, this guy, right? And then the next slide that you have, which is this guy, the next one this one, this whole thing, just use a different color marker. So this whole thing is the same as what you have over here. Same thing as this one, right? This one. Here you have W subscript big N over 2, right? Because for this entire thing, big N is 8. For that reason, this is W subscript 4. This is W subscript 4 as well. This is W subscript 8 over 4. This is 2, right, in this one. Clear? Questions till this point? So you can see, you started with an 8-point DFT. You broke it up into two 4-point DFTs, right here. This was two 4-point DFTs, right? And then you broke this two 4-point DFTs up recursively further into two 2-point DFTs, and we know what is the 2-point DFT. Clear? Okay. What else do we have to discuss? Discuss that, and that. Okay. Now the same algorithm, you do not need to just leave it for, you do not need to have it just for 8-point DFTs, right? The same algorithm, you can have it for 16-point DFTs. In that case, those 16-point DFTs will be first broken up into two 8-point DFTs, and then those 8-point DFTs will then be broken up into two 4 points, and those 4 points will be broken up into two 2 points, right? You can have it a 32-point DFT, you can have a 64-point DFT, you can have a 1024-time DFT. It's the same process. You just do it recursively. Clear? Now, you might have noticed that this output is coming in a different order, right? So how do we actually keep track of this, right? So what is the shortcut to keep track of that? So to understand how is that happen, so you can write the index, the original index of the original order in terms of decimal digits, and then well, let me get it. So when you did the first split, the output order was 0, 2, 4, 6. Then we did the second split, the output order was 0, 4, 2, 6 and 1, 5, 3, 7, and then third split did not really change it. So how we can remember all of this? We can write the original index in the form of binary values. For example, if it's an 8-point DFT, you can write it as 3 binary values, right? 3 binary numbers. So 0, 0, 0, 0, 1 is 0, 0, 1, 2 is 0, 1, 0, 3 is 0, 1, 1, and so on and so forth. And then after doing all these divisions, right, the final split will be in the order in which these bits you can reverse them. So 0, 0, 1 you can reverse it to make 1, 0, 0, and that will be the same index as what you will get at the output. 0, 1, 0 will stay 0, 1, 0, 0, 1, 1 will become 1, 1, 0, and 1, 1, 0 in binary, if you convert it to decimal, is 6. 1, 0, 0 is 4, 0, 0, 1 is actually 1, and so on and so forth. So no matter how big the sequence is, you can just figure out which index does it correspond to. Is that clear? Clear. All right. Now let's do a quick example. So let's say you have this example in which you have these values: x of 0 is 1, x of 1 is 2, x of 2 is 3, and x of 3 is 4. Right. So how you can do the same thing? You can just write the values over here, right? 1, 2, 3, and 4. First, you get the sequence A of n, which is x of n plus x of n plus n over 2. You combine the index at 0 with index 0 plus big N over 2. Big N in this case is what? What is big N in this case? 4, because there are 4 points, right? So you combine the input at index 0 with the input at index 2. So you get 1 plus 3 is 4. Similarly, for the second entry for the sequence A of n, you have 2 plus 4, that is 6. Then you get the sequence B of n. So 1 minus 3 is minus 2. Then you have 2 minus 4 is minus 2, right? And then you multiply them with w subscript n to the power n. So w subscript 4 to the power 0 is 1. W subscript 4 to the power 1 is minus j. For that reason, this became minus 2 times minus j, it becomes minus 2j. And so that was like the first split, right? And then you have a 2-point DFT. Just add the 2 inputs, you get the first output, which is 10. 4 plus 6 is 10. And then you add you subtract the second one from the first one, you get minus 2. Then similarly, you do here, add the 2 inputs, minus 2 plus 2j, and you have minus 2 minus 2j over here, right? And then you multiply with w subscript n to the power n. So in this case, this is just to the power 0, that is 1. And then the outputs are 10 minus 2 plus 2j and minus 2 minus 2j. But then what are these actually? So you can just write the input indices in the form of binary digits, and then just flip those binary binary numbers, and then that will give you what indices, what outputs are you getting. And if you see the number of complex multiplications, is w subscript 4 to the power 0, which is actually 1, but it's not really complex, but you can think of any real number as complex as well, right? So the number of these multiplications, you have 1, 2, 3, and 4. So you have n over 2 log 2n, so n was 4, so 4 over 2 log 2 4 was 4. So in place of having 4 times 4, that is 16 complex multiplication, just have 4. Clear? So this concludes FFT, right? However, before we just completely hand off from here, right? You can use the exact same algorithm to compute the inverse DFT as well, right? So what is the formula for the inverse DFT? Let me just write it, and then that will help you understand how we can do that. Okay. So the formula for the DFT, we already know what is that. You have an n-point sequence x of n, go from n going from 0 till n minus 1, w subscript n to the power kn x of k, right, where this this k goes from 0, 1 up until n minus 1. Okay, so this was the definition of DFT. What is the definition of inverse DFT? This is just the sequence x of n. You can get it from its corresponding coefficients in DFT. Just have 1 over n. The sum, I have k goes from 0 till n minus 1, x of k, w subscript n to the power minus kn. Yeah, and this is for n going from 0, 1 up until n minus 1. What I can do, I can just do a slight modification. I can say w subscript n, x of n equals 1 over n, k goes from 0 till n minus 1, x of k, and in place of w subscript n to the power minus 1, I can just write w subscript n tilde kn, where again n goes from 0, 1 up until n minus 1. So this is the definition of the inverse DFT. This is the definition of the forward DFT. Clear? Now if you compare these two, they are very similar. Now here the sum goes over n terms, here the sum goes over n terms. Here you have x of n, right, which is what? Which is just the value of the signal x of n at certain value n. Here you have x of k. Here you have w subscript n. Here you have w tilde subscript n to the power kn to the power kn. For the computer or the DSP processor, it doesn't matter, I mean, what you put in. So you can, if you can make this sum look something like this, right, you can also make this sum look something like this. So you can use the exact same algorithm to compute the inverse DFT as well, right. But what you do, you can, let me just copy it here. You replace w subscript n with w subscript n tilde, right. In place of having the input signal as the input, you have the DFT coefficients as the input, and at the very end you just divide by 1 over 8, and then you will get the signal as the output. And the output order, it will be changed in the same way as in the forward DFT. For example, you get x of 0, 0, 4, 2, 6, 1, 5, 7, 3, 7. For the 8-point DFT, you get 0, 4, 2, 6, 1, 5, 3, 7. So you have the exact same structure, just replace w subscript n with w subscript n tilde, and you just divide with 1 over 8 at the very end, 1 over n at the very end. So this way you can use the FFT algorithm to also compute the inverse. Yeah. So this FFT algorithm is a key with which we can compute or do the frequency analysis of discrete time signals. If we had not developed this algorithm, we cannot do that, because otherwise it would not be tractable, the way we compute the DFT of signals. Clear? So I am on the dot, finished, right? Any questions? All good? So I guess I should stop the recording. If it is still running, it is still running, so I'll stop the recording. Thank you guys. Right, take care. Bye bye.